So complex for me, okay, it's just a vector space where you have an odd operator, a Z2 graded vector space, where you have an odd operator that squares to 0. It is not the, so it would play the key role. So previously, so do you hear me?
Yes, we do.
Okay, good. So previously, people, previously there was no complexes in physics, like 80 years ago. But then people started studying systems with gauge symmetries. And while they were fixing these gauge symmetries, they introduced so-called BRST operators, and complexes started to appear in physics. However, it is the historical place where complexes appear. I think that now, based on our experience with so-called topological theories, we may say that we should assume that vector spaces are complexes from the very beginning. And let us look. Let us look at the main axiom. This is the axiom of total closeness. And let us consider particular cases of this axiom. So for simplicity, let us assume that Q is 0, okay? Then closeness means that di equals to 0. What does it mean that di equals to 0? Since I is a differential form and not just a function, it has different components. It may have lower component, that is a function. And the function is closed only if it is a constant on the connected component. And this is an old understanding of what does it mean to be topological. So 0 component of I depends only on connected component of the space of geometrical data. So okay, now it's interesting that I has higher components. You may ask, why do we need these higher components? And the answer is, one of the answers, why we should probably have higher components, is because that we may consider quantum field theories on so-called Feynman diagrams or string worldsheets. So when I talk about Feynman diagram, I mean a graph, and not just topological graph, but a rather graph with the lengths of on edges. These lengths of edges are called in the 50s, in the end of 40s, so-called Schwinger times. And they correspond to internal time of a particle that is moving along there. So when we go from particles to strings, instead of Schwinger times, we get even more complicated object. namely moduli space of complex structures. Then we want to compute some answer. And this answer is an integral over these spaces. Either integral over the space of Schwinger times, or integral over the moduli space of Riemann surfaces. But if we want to integrate something, it's better that this should be a top differential form. So the procedure would be like this. First, we produce this I, then take out of it proper differential form and integrate. So it's very different from topologicity condition. And it is this condition that is behind the string theory of type B, and it is basically in the string theory of type A, and it is also in the understanding of contribution of the Feynman diagram, not just as an element of the linear algebra, where we have incoming particles, outgoing particles, but also with what physicists used to call one-dimensional gravity on the world line of particles. We will come to this later. So, in order to make such constructions, we definitely need to have I to be a differential form. And I need to comment on what I say higher. So I heard it from John Byers 16 years ago, when he explained to everybody, and I was in the audience, that higher mathematics is related to standard mathematics in the following way, that standard mathematics deals only with connected components, and higher mathematics deals with the homotopy groups of the corresponding space. So he said, so it was, so okay, now I can write. Now I am explaining why higher. So I explained differential forms because we need to integrate, and now I'll explain a bit why higher. So let me repeat Byers. Byers says, is either trivial or a lie. Do you see this Byers statement that A equals to B? Лёва, видно?
Да.
So if A is B, that is trivial. If A is not B, it's a lie. So Byers says, no. We need to put here equivalence, gamma. than this, that A is equivalent to B with respect to equivalence gamma is meaningful. So let me put here the bias picture. A, B, C. So he proposes to think of A, B, and C something like something that lies on some spaces, actually the equivalence classes. And he proposes to write down paths. So we cannot make a path from this component to this component. So in this sense, A is not equivalent to C, but A and B are equivalent. Okay, so now we understand what does it mean to be equivalent. But then he says, look, in this example, we have two equivalences. Are these equivalences equivalent? So it was the notion, idea of bias. It could be that there is an equivalence of equivalences. And he says that it is what we should study in higher mathematics. So in particular, if this is like a torus, then gamma and gamma tilde are equivalences, but they are not equivalent. And so on. So in this way, bias says that that we should start this hierarchy. And from my point of view, it means that instead of P naught of some space, we have homotopy groups. And some approximation to these higher homotopy groups are cohomology. You see, connected components are classified by locally constant functions. So it is an old meaning of the word topological. But here, we may see how topological they are. So somehow it is a second motivation. You see, it's a bias idea that you should never, that there should not be a statement that something is constant. In higher mathematics, it is a wrong formula. You see, let me compare it with physics, with mechanics. In mechanics, if you are on flat space, you can say that acceleration is 0. And it's okay on the flat space. However, if you are on the curved space, acceleration is not a tensor. And so you cannot formulate physics in terms of acceleration. So somehow here, condition that something is locally constant does not fit into philosophy of higher mathematics. So if something is locally constant, we should see, hey, most probably this is the lowest level of more conceptual things, of closeness of some differential form. Okay?
I mean, I have a comment.
Yes.
So maybe a good example here is, at least for me, is the thing which is called Chromological field theory. Like in Gromov-Witten invariance, we have action of the space of cohomologies of the cohomologies of the space of configurations or of modular space of Riemann surfaces on something, and from the standpoint of just topological field theory, we would have only the action of I mean, only the action of one, basically. So we would count how many curves pass through a number of points, but we wouldn't act by cohomologies of the space, and we can. So it's just more information in addition to the base level.
But you see, the Gromov-Witten theory, of course, came from string theory, in some sense. Because before Witten studied twisted string theory, there was no such theory as Gromov-Witten theory. Main thing was that the main objects should be differential forms on the moduli space of complex structure. And this thing has had an origin from physics.
I mean, I'm just saying it's already, in the example of Gromov-Witten theory, the structure is already here.
Of course. So Gromov-Witten theory, of course, is an example of such structure. However, here you still have differential. So in Gromov-Witten theory, okay, good point. If the would differential be zero, we would have Gromov-Witten theory. It's a collection of differential forms.
Of closed differential forms, so we can consider them as cohomology classes instead.
Yes, of course, since they're closed, not just collection. So with zero, it's like this. However, it's important that we do not need to consider, okay, let us come to Gromov-Witten theory. So Gromov-Witten theory, let us discuss it as an example. I'll draw a picture. In Gromov-Witten theory, you consider maps. From the source or the worldsheet. If you are a mathematician, you call it source. If you came from physics, you call it worldsheet. So here are the maps. And here are, say, points. And condition is that points number 1 should be mapped. To the cycle C1. And point number 2, oh, sorry, different color. You see, now I can do it like this. Should go to the cycle C2. And here, it's a map from the source to the target. Now, interesting. Why should we necessarily consider these objects as being cycles? We may easily consider them as being chains. Yes, there are chains. And if there are chains, the problem becomes a bit different. So you are mapping something, the image goes along the cycles, and you get your beloved enumerative number. But when the image hits here, the point can drop out of the cycle. So what would you say? You would say that you are losing this topologicity. Actually, it's no, you are not losing it. You need just recall that this enumerative problem can be formulated for the chains too. But the fact that it's formulated for the chains is captured in this Q. So if you have special Q, you can understand why this thing is not constant. It's because it has a right-hand side. So while the right-hand side is non-zero, you can have non-constant object. So it's a pity that people never studied Gromov-Witten theory in this way. No, it's really a pity because one should speak about chains and write down corresponding relations. So, Lyova, you know that in Morse theory we can do it with chains, right?
So, yes, indeed. And
so,
like, you can kind of do it in Gromov-Witten theory too, but
we did not.
But we did not.
We did not. Okay, we did not. Then the question would be why we did not. It's because Witten did not tell us to do this. Because in Gromov-Witten theory, we say that observables correspond to differential forms, and Q on observable correspond to the RAM on differential forms. I put it the RAM X because this is differential form on M. Target would be Y on Y. Then equations would be a bit different. But look, who would ever consider chains in complex geometry? Nobody is doing it. However, in the context of quantum field theory, it's very natural to consider non-trivial actions of Q on observables. And actually, that's what I recall. Observable comes from the boundary. And if you correspond complex to the boundary actually carries the structure of the action of Q. And since local observable are coming out of boundaries in this Dirac-Segal definition, they should inherit the action of Q. So I was not discussing it right now. Maybe it will be more clear if we consider one-dimensional example. But first I am trying to answer the questions. So I got the following question. Why we have Q? Okay, I would say by examples, it's kind of an answer. It is the inductive and not deductive procedure. By considering different examples, we may see that we need to have this Q. And the Lyova says there is an example. Maybe there are other questions. So after all, it was about cobordisms and that stuff.
So the I could be a sum of differential forms and integrate
Yes,
on.
Yes, of course. But for me, sum of differential forms is also a differential form.
Yes.
I do not consider differential form as being of pure degree.
Okay. So then you can integrate over space with the boundaries.
If you have differential form, you can integrate over, of course, you can integrate over space with boundaries.
Yes.
The question would be, what would you get? Then the integral of such differential form would depend on something, and we know.
Yes. Mm-hmm.
Moreover, this thing has an application in so-called, so what people used to know? People used to know so-called Kontsevich deformation quantization. So actually this theory of Kontsevich deformation quantization is the following construction. You have some type of input, then you make a differential form on the configuration space, and you prove that this form is closed. So you get exactly this. So Kontsevich construction is exactly producing all these differential forms on the configuration space. So this is an answer. And it is topological in the sense that it is closed.
Mm-hmm.
So actually it is the basic. So what we are discussing right now is the basic notion. And it is interesting or important that this notion was mostly overlooked several times. Let me make an extra comment that maybe would help you to understand what is going on. So my idea is to convince you somehow that this is the right formula. So remember, so it's easier to be convinced in dimension 1 than in dimension 2. In dimension 1, we know that quantum mechanics is something like this. Now, everybody knows that you never study an object alone. So Bayes did not told us this, but it's very clear. You should study objects in families. All right? So this H is an element of the endomorphisms of V. In other terms, it's an operator. the question, how can we deform an operator? Leva.
Yeah.
Do you know how to deform an operator a little bit?
Like, what do you mean?
How to deform an operator?
I mean, I think I know what answer you expect me to get, but
you have a matrix. How can you deform a matrix?
Okay, let's say I can add something small, and
exactly, you add to it a small matrix, right? You see, if you want to deform something complicated, like complex structure, you are using Beltrami differential. But if you are deforming something simple, it's easy. So in particular, just imagine that you have equation. It's some just polynomial equation. It has coefficient. How do you deform polynomial equation? You add to polynomial another polynomial with small coefficients, right? So matrix elements are actually what? Matrix elements are parameters. So if H is A, B, C, D, then this 2 by 2 matrix, then H has 4 parameters. How to deform it? Delta H is, of course, delta A, B, 0, 0, 0. It's delta A deformation plus 0, delta B, 0, 0, right? So you deform this by deforming coefficients. So you deform H by adding to it another linear operator. Let me call it epsilon or delta H. So it is just linear operator that is small, say in sense it is the standard norm, just small. So this is the deformation. So delta I is this one minus this one. So now you may ask a question. How to compute this difference in the leading order of deformation? So it is exponent of the matrix. However, so one of the ways to do it is to expand it and group terms together, compute, and you will get an answer. That's how mathematician would do it, right? E to the A plus B equals A plus B to the power n over n factorial sum over n, right? So it starts with this term plus structures like this: A to the power k b, A to the power n minus k minus 1, sum over n, sum over k, starting from 0 and ending up to n minus 1. Okay? And if B is small comparing to A, we can omit what goes on later. So for mathematician, this is just a combinatorical problem. However, all physicists know the answer. And let me give you the answer that all physicists know. All physicists know that this may be written as integral from 0 to t, dt tilde e to the t minus t tilde h delta h e to the t tilde h. Huh? So not everybody knows this formula. However, all physicists used to know it. There are many ways to prove it. One is to use this combinatorics. So
here you assume that delta H is infinitesimal, right?
Yes, yes. So here I put plus O of delta H squared. So here I assume that, so here I do not want to take contribution of b squared term, of 2b's. O of b squared. I can put it like this. I can put here, if you prefer, I can put here epsilon. I keep epsilon here, and here I will put O of epsilon squared. Now this formula would be mathematically correct. So this is formula, and I can also do it here. And here is something, as people say, what physicists used to write, epsilon squared. Now there are two formulas. Formula 1 and formula 2, two formulas. And an exercise is to check that that formula 1 is correct. Why I like formula 1 is because that formula 1 has an interesting meaning. I'm rewriting this formula. And now I have the following picture. Now 1 from a formula turns into something that can have analogs in different dimensions. It says that in order to deform the main object, you need to put observable, delta H, operator is observable, and integrate the position of this observable along the integral. But this object, to be integrated along the integral, has to be what? Has to be a one form. You integrate over the position of the point on the interval. You may say, okay, this is peculiarity of what? This is peculiarity of one-dimensional situation. Actually, the answer is no. It's not the peculiarity of one-dimensional situation. One-dimensional situation is an example of the very general idea. Suppose you have the cobordism corresponding to the main object, and you have a point P with something that we call operator here. If we somehow integrate over sigma, this is the deformation of the cobordism. Good formula, good picture. Take a local observable, integrate over, and you will get the deformation. You may ask, how can we prove it? How could such statement be proven in such generality? And the answer is very simple. You just need to consider the main equations. And you may check that the main equations would be satisfied. Okay? By the way, you may ask, what are the main equations for cobordism? So the main equations for cobordisms are, of course, quadrics. So I think it's my fault not to mention it here. So I wrote the main equation in the form of this type. You may think that this is quadratic because it's I, and this is linear. Actually, the main equations are consistency conditions here. You may cut this guy either along this line or along some other line. And the result should be the same. So here we have a red cut. And here we have a black car. So answer should not depend on when on where I cut. So equations are basically quadratic equations. You may say, let us define thing on so-called pens, like here. Let us make this more complicated cobordism from simple cobordism. But we can get it in several ways. We need consistency condition. And this consistency condition means that you have relations between red cuts and black cuts. That should be the same. So actually here we have infinitely many quadratic equations. In dimension 1, it is the following. E of T1 plus T2 is E of T1 times E of T2. E of T1 tilde plus T2 tilde should also be this. I'm sorry, I have to erase. I have to erase the middle. Then just imagine that T1 plus T2 is T1 tilde plus T2 tilde. Then these would be the same. And I have quadratic equation. Okay? Or in other terms, E of T minus, what is another letter? Tau times E of tau should be constant. Should not depend on tau. So picking two different taus, I have quadratic equations. I can try to solve them. And it turns out that here there is a universal solution. Just imagine that that what you will have if you integrate this P over this cobody. So when I wrote it this way, it is topologically not very different from the interval. So if you understand how it comes from the interval, you would understand how it comes out here. You just need to prove this analytic formula heuristically. So in other terms, I'm trying to explain it to you in different ways. You want to deform. Okay, now I'll erase this. You want to deform E of T1 plus T2. That is E of T1, E of T2. Put deformation here and use Leibniz rule that it is delta of E of T1, then you have E of T2 plus E of T1 times delta I of T2. Then here, but you can solve this because here you have a point going along the first interval, and here we have a point going along the second interval. Well, that's it. That's how you deform. And this thing is universal deformation by zero or point observable. It's better to call it point, local. Sorry, by local. Okay. If it's not convincing this way, let me violate my rule not to bother poor Feynman and say that this deformation by local observable is realized if we believe in functional integral. It's not a proof, it's an illustration. Proof could be done formally. Suppose we have e to the integral of Lagrangian on sigma. And here are some fields. So what does it mean to deform this guy? You are deforming Lagrangian, and then you expand. Okay, I put it. I would like to write down correct formulas. So if you heard about Lagrangian a little bit, you may see that what's written here, at least formally, is the insertion of local observable at some point on sigma. And then you integrate. And then you take this integral out. So it's called deformation by local observable. This thing does not mean that functional integral dominates. It is just a representation of this idea. But the main message here is that there should be objects associated to the cobordism with a marked point that would allow you to integrate over the position of this point. And this corresponds to deformation. So it's another motivation to study what I called higher theory. So deformations of the theory are in higher theory. So the good news here is that deformation in such formulation of the theory are internal. And as a mathematician, you understand that internal things are much better than external. You deform theory from itself. Okay, so this was my comment. Leva.
Oh, this thing I know, and my problem is I do not really understand what the local observable is. And you can maybe read what I wrote in chat, because like this, I wrote down something.
Okay, so let me explain what the local observable is. First, general picture, and then application to one-dimensional example. Okay.
Can we have a like
break?
Some kind of definition?
Definition, yes.
Like I gave I want to state that I gave some kind of definition, and I want to know if it is correct or not.
So that's what I briefly discussed in the talk, but this is kind of important thing, and I actually would like to give a definition of local observable. Exactly.
So let me ask if what I'm saying is correct.
Yes, please give.
So, okay, so I want to have a function, or maybe a differential form, I'm not sure, from the geometric data on a pointed ball.
1 second, I'm sorry. Yes.
So I will have a function on the geometric data on a pointed ball. We have a pointed ball.
Okay. Suppose
we have some geometric data on it. Some geometric data, but okay, radius is okay. So, and I have a function or differential form with values on V of boundary of this ball. And it is a function or differential form of the geometric data. And then there is a consistency condition, which states that if I cut smaller ball from this ball, then it should be consistent. And then I need some kind of closeness condition, and I do not know how to say it. I would like to.
Exactly. So it's not exactly true. Well, let me tell you what actually happens.
So, okay.
So actually, what actually happens looks as follows. You have some big object. I will write it as U with boundaries. And this object is called sigma. And this boundary is called X. And this boundary is called Y. And you want to do what? You want to define the following object. So that's what we want. That at some point P, we should expect to have some object called O.
And I can put it in any point, right? So, yeah. So it is the same object if I put it in any point.
And we would like to define this thing.
So is it like a point or a framed point, where do I put it? Or maybe coordinate chart around P?
So I'll try to explain how to put it at P.
So just P, okay.
Or maybe you're right, maybe. So let us first try to put it at P, and actually it would depend on the geometrical data near point P.
Yeah, that's what I'm saying.
So the output would be that this picture should correspond to an element that should be called I sigma O P that should belong where? To home. In this particular case, home V of X to V of Y, and times maybe some function on geometrical data.
On pointed geometrical data.
Yes.
So geometric data with P. Let's put it here. It is important.
Data P, yes. Of course. So we take sigma, O, P, and some geometrical data, of course. So I used to write it G, O, P. So what do? We do the following procedure. We pick up a point P. Then we cut out a ball of radius r small. So now we will have E that depends on what? On sigma, on G, on P, on R. That belongs into this tensor product. But now it has additional boundary. And let me call this boundary BR. VBR. Okay? Due to main axiom.
Sure.
So here I would even write it in a better way. I will say sigma minus B, P, R, and G belongs here. Because we have additional data.
You should maybe call it boundary of BR.
PR, it means that it has a center at P. And
I mean, you should write boundary symbol here on the right-hand side.
You are absolutely right. Boundary. Thank you. Boundary. Of course, boundary. Now, what I do, so now I want to transform this guy into something else. You see, since I want to make out of this something that I'll call space of observables. And of course, I assume that R would tend to 0. However, it is hard to tend R to 0 because these boundaries are different. When R is changing, the sphere is changing. That's why I will take another object. It's a family. VR. That would belong where? It's a map.
So
from some interval to V dual of DBPR. So consider maps. That I call VR. So these maps are families. So for each R small, you have an element in the space dual to the vector space associated to the boundary. Okay?
so, and it also depends on P, or you want to say that it actually doesn't?
At the moment, P is fixed.
Okay, okay.
Then I say, so belongs, so it's just a map. Good VRs are such that contraction with the VR of the VR with this object so this thing belongs where? It belongs here. And it is also belongs to functions on R on an interval. Okay. So if I plug it here, I'll get this object. That is function on this interval. Okay. Oh,
I mean, that is basically, I think it is equivalent to saying that I can change the radius and compose and compose with the map which is obtained from the annulus.
I haven't finished the definition of good.
I mean, it's not dependent on this, right?
No. So it's so these maps are good if are good VR are such that there exists a limit R going to 0 of this expression.
I'm not sure. What if instead of doing this, I will consider two different radii, R1 and R2, two different balls, and then the map which corresponds to the difference between these balls.
First of all, you need to identify the vector spaces.
I mean, I can do it because I have the map.
But it is this map. So you want to say, so what you are trying to say is that, you see, what you want to say is, let us choose this R very small and say that if it's very small, we can neglect that it is different from 0.
No, I'm not trying to say this. I'm asking, there is a, for two radios, possible radios, there is a map from one V to another one.
Of course.
Which comes from this difference of these two balls.
There is this map, but then you can just take this V, so you can identify V's here and here. You can do it. You can, using this map, you have a parallel transport. But it doesn't help.
But isn't it the same as, like, just by factorization property? I think that if you pick the family which is parallel with respect to this transport, then it will have a limit.
No.
Like parallel or almost parallel.
No, of course not. It couldn't have a limit because this thing lives in different spaces.
I mean, we have identified them.
But then, but if you identify them, then any vector goes. Any vector from the mega space goes. And it would not be proper answer in dimension bigger than 1. And this is kind of mistake. I think it's a mistake. In what Costello and Guillen say.
So can you give a minimal example where minimal example when it's not correct?
Two-dimensional example.
So two-dimensional, yes. Can you like?
In order to give this example, okay.
So just what is the geometric data? What is
minimal example when this thing is wrong is two-dimensional conformal theory. So the fact that this is that you do not need to do this in dimension 1 is a low dimension peculiarity. But if you try to follow my definition, look.
So I do not understand how it is different. I do not understand how it is different because so imagine I have this this sequence of or family of vectors for different r, okay? And suppose they are identified by this transport. Then I think that the correlator will be the same for all the different radii. So I will get a limit.
You cannot say that correlator is, so you can, so what you are doing is you are just replacing shrinking by unshrinking. But it's not a definition. If you just replace shrink by unshrink, you will not get anything local. So you say, let me shrink, but take here such vector that it comes from unshrink. It means that you are not shrinking at all.
No, I think that.
So I'm trying to follow your proposal. By the way, you may see that your proposal is not working even in dimension 1. Okay.
Excuse me. How it's?
So in dimension 1, you have a ball.
Okay? Yeah, sure.
So the boundary of this ball consists of 2 points.
Yes.
1 point and another point. So actually you want to put operator somewhere here.
Yes, yes, sure.
Okay. So
that's the vector on the boundary.
So if I follow your proposal, you may say take any operator here, and it will be the result.
No, no. Take such operator that it comes from arbitrary small ball by the transport.
Okay, so let us compare 2 situations. Okay.
Yes.
Here we have
sure.
T1, T2, T1 plus tau 1 T2, and here we have tau 2.
Yes, sure.
So if you, you can take something that belongs to V star here. So it's an operator.
Yes.
Let me call it OR. That you want to put here.
And I want it such that it comes from.
Then what is the operator that you are going to put here?
Such operator that.
I think you want to put here the following.
Yeah, something like this, right?
Yes.
Something like this, up to the signs and orientations, something like this.
If you put this operator here, then this expression would be exactly this expression.
Yes.
And it doesn't mean that you are not.
But that's exactly the point then.
That you are not shrinking anything.
But wait, this gives me the sequence of operators which give the same answer. So like by your definition, the correlator is the same, right?
Yes, but it means that you are shrinkingable, and then you pick up such vector that it is equivalent to unshrinkingable. So it means, of course, it gives the same answer, but you are not doing anything.
But I mean, that's the point of not. So. No, and on the other hand, if you have a sequence of these operators, then you can obtain, which has a limit. So do you mean that this is, I mean, is it correct that in this way I will obtain an example of the local observable? And you are saying that there are other examples.
So if you consider this, you will obtain, yes.
So the point is that the sequence can be.
So in this way, you will obtain, but this way is not that way.
But I mean, this is it true that this is a particular case of your definition?
In dimension 1.
In any dimension.
In any, I would say that you would not get locality.
But I will, because I said that I will get it should come from arbitrary small ball.
No, because then you will have problem of cutting somewhere here.
I do not understand. I'm sorry. I just don't understand what's.
You see, of course, you understand what is the answer that you would probably want to get. You want to have an operator standing here, and this operator should not depend on the initial size. You want to have something local. But in your definition, you are involving this identification between bigger and lower radius. In this sense, your definition is not local.
But because this, I don't understand how it's not local if it's about arbitrary small ball. How is it not local?
So you want to say, but still you need to compare two things.
But I have canonical identification coming from the
canonical identification brings you these points back here.
So I have the canonical identification of the boundary spaces, right?
Yes, but
so I can call this call this space local. I will pick a point P, and the let me say projective limit of these spaces while R tends to 0 is my space of local observables, right or not?
No, because you are giving because in the definition that you are giving, if you contract your thing here, you will get constant sequence.
So, okay, constant sequence has a limit indeed.
Yes, but it's not interesting. It means that that you have done nothing.
So you're saying there are other examples when what happens when there is some sequence which gives which cannot be made constant and still gives interesting limit,
so,
right?
Yes, I want to say that you may consider this, what I said, another sequence, not sequence that undoes things. Consider sequence. Consider sequence, and consider sequence such that there is a limit. And then what I prefer to call local operator is of course insertion of the equivalence class of good VRs. So I am giving different definition. So local operators are coset of the good VRs over nil VRs.
Okay, so it is indeed the projective limit of the spaces, but with respect to the weak topology induced by correlators.
Yes.
Okay.
And,
okay.
and I say that this
for me.
that this is a local operator.
Okay. So
if you want me to give you a sequence,
and still the full procedure is localized in some ball. So I do not really need to know the whole space.
Of course, because the output of this procedure is not a vector. So for any coset space of local operator, you define this correlator. It's a correlator that you are defining. So you have a map from local operators into this correlator.
So I still have a lot more issues. Okay, I'm sorry?
It's very different. It's not the space of vector spaces associated to balls. So these are two different spaces.
I mean, I'm okay with the fact that it is projective limit with respect to the weak topology. It's okay. So now I still have more issues with geometric data, with framing, and with the position of P. So how can I check that it is the same O in the different points now? How do I do it?
You see, of course, you cannot. Of course, this procedure. Of course, this procedure. Good point. This procedure explains you what is a local operator at a point P that depends on the metric G around this point. And of course, if you ask, could it be, if you ask in which sense two different local operators are the same, I would have to tell you that in general they are not the same. In this definition, local operator could depend on metric at a given point, and metric could be different at two given points. So the only way to say that they are the same could be made only by diffeomorphism, when you take one point P into another point P.
So,
and if diffeomorphism preserves metric, you can say that, now I see how to identify that.
So let's assume we don't actually have metric and have, say, complex structure.
So
then this procedure still will have some symmetries.
So this procedure actually means that for a sequence of balls center of P, you have something that being plugged into this hole, it gives the same limb.
And so to put it in every point P, I will need a coordinate chart in P, so I can plug it in, right?
So if you measure the distance in terms of coordinates, then it will depend, of course, on coordinates.
So I mean, I just want to integrate over the positions of P. How you that's exactly
Yeah,
how you propose.
But at the moment, I only explained to you how to place something local. And the second question is how to integrate over the position.
To integrate, I will need to put the same object in P, in every P. That's my problem. So, and right now, as it is, it depends on coordinate chart or something like this. Maybe framing, maybe some, I don't know.
So I think
maybe we should state that it is invariant on this coordinate chart, or like we need something additional.
So you want to say, you know, it's a good point. So the fact that I know how to integrate in particular examples does not mean that I can explain it in full generality, because
I mean, if it does not depend on coordinate chart, you have some kind of invariance, then you definitely can integrate. But I think I'm not really familiar with conformal field theory, but I think that conformal dimension, non-zero conformal dimension basically means that it is not invariant.
Yes. So actually, in order to integrate this thing, you need to add geometrical data. Unfortunately, it's an answer.
Framing.
Maybe framing, maybe the jet of coordinates.
Okay.
So that's what people used to say in Lagrangian approach. When you say that you need to multiply the local expression of fields with the corresponding power of the measure. Okay, I think now we need to make a break. And thank you very much for this remark. And later, I will try, I consider this as a good question, how to integrate. And later I'll try to reply. Okay, so what time is it now?
5:30 p.m. Moscow.
5:30 p.m. Moscow.
Yeah.